Today we are going to talk about this notion of curvature, negative curvature, introduced by Gromov. So first, let me mention what would be the content of today's talk. So the content will be, first we will be looking at introduction and some examples. Then we'll see the behavior of geodesics and quasigeodesics in Gromov hyperbolic spaces. Uh, then we will see an uniformization technique for Gromov hyperbolic spaces, which is known as the BHK uniformization. BHK stands for Bong, Heaven, and Koskela. And then we will see some more examples by considering some intrinsic metrics that we are familiar with in complex analysis. So this will be so I will restrict it to the uh, hyperbolic and quasi-hyperbolic metric. I will mention some references for other kind of metrics such as Kobayashi and Carré. Okay, so we can start now. Okay, so let us look at the Poincaré disk model of the hyperbolic space. So, and so if you see the geodesics in this space, they are basically the arc of a circle, which is orthogonal to this unit circle. And if you make a geodesic triangle, so let us say this is one such. Okay, so this is a triangle. Okay, so what we are seeing is that basically geodesics are getting geodesic triangles in this space are basically slimmer than their counterparts in the positively curved spaces. So these geodesic triangles, the sides of this one is getting is kind of they are slim. I will mention what do you mean by slim. So, and this is kind of observation. Basically, if we see geodesic triangles in spaces with varying curvature, uh, we will see that a pattern something like this will be in positively curved spaces, and this is obviously flat, and in negatively curved spaces. So this is positive, flat, and this is negative. Okay, these kind of pattern emerges in the geodesic triangle. Okay, in this varying curvatures. So basically, Gromov and Rips realized that the large scale geometry of the negatively curved spaces can be captured by the property that all geodesics are basically slim. Okay, uh, and taking this slim triangle as a defining property, this leads to the notion of Gromov hyperbolic spaces. Okay, so just a rough idea of how geodesic triangles we are going to see uh, in Gromov hyperbolic spaces. Okay, so here's our definition. So basically, Gromov introduced this definition in the in the setting of geometric group theory, and I will mention the like metric space setting. So let x comma d be a geodesic metric space and a geodesic triangle. So geodesic triangle basically will be the union of geodesic segments, geodesic, let us say gamma I from ai to b to this x, which is, and obviously this they have the same endpoint. But what does it mean? Is it means that gamma 1 of b1, where the first one terminates, the second one starts. Means gamma 2 of a1 and gamma 2 of b2 is basically equals to gamma 3 of a3, and gamma 3 of b3 is basically equals to gamma 1 of a1. Okay, so and these gamma i's are basically the sides of the triangle. Okay, okay, so okay, so geodesic metric space, geodesic metric space x comma d uh, is said to be is said to be delta hyperbolic uh, if if every uh, if every geodesic triangle if every geodesic triangle in X is delta slim. What does it mean? Basically, delta slim means that is any, if you take any side of the triangle is contained in the delta neighborhood of the union of other two triangles. Okay, so I hope this is clear. I will just picturize it, and a metric space and uh, geodesic metric space x comma d is said to be Gromov hyperbolic. Be Gromov hyperbolic if it is delta hyperbolic for some delta greater than equals to 0. Okay, so if you see this one, this definition means that, suppose, let us say we have a geodesic triangle. Okay, if you take a delta neighborhood of this side, let us suppose delta neighborhood this side and delta neighborhood of this side, let us say, okay, and this side delta neighborhood of this one. Okay, it doesn't look that it is delta. So basically it says that the third one also contains in this neighborhood. Okay, like as you can see here, the way I have constructed this triangle, it is there in the union of the delta neighborhood of other two sides. Okay, so this is a delta neighborhood. Okay, so this is what we mean by a slim triangle. Okay, so I hope it is clear up to this point. Okay, so we'll immediately see some examples. Example 1 is basically R with the obviously the norm distance like x minus y. R is 0 hyperbolic. This is quite easy to see because if you take any on the real line, say x, y, and z, and the geodesics are basically the line segment joining these 2 points and this one, and the geodesic joining xz will be x to z, this line segment. So basically, what we see is that any one of the 3 sides is a subset of the union of the other 2 sides. It means that this xy is a subset of uh, xz union yz. Obviously, it is a subset of xz only, and xy is a subset of yz is a subset of xy union xz, and xz is a subset of xy union yz. Okay, so and therefore each side lies in the zero neighborhood of the union of the other two sides, because it is already contained in that. It is already contained in the sides in the union of other two sides. Okay, so this is the first one. Example 2 is again quite easy to see. It is uh, any bounded metric space is Gromov hyperbolic. Again, this is easy to see. Just take the diameter, which is, let us say, less than equals to k, and you take any delta greater than equals to k. So obviously that will if you take the delta neighborhood of any union of any other two side, that third side will be contained in that. That is trivial in this sense. This is a non-example 3, which says that Rn is not Gromov hyperbolic for any n greater than equals to 2. Okay, so basically what's going on in this one is that you take a triangle and let us assume that that triangle is delta slim. Okay, so what we can do is that we can just scale the triangle by a factor c, and the new triangle, let us say ct is will be c delta slim. Okay, and letting c tends to infinity shows that R2 is not delta hyperbolic for any delta greater than equals to 0. Okay? Because we can take a large triangles in the Euclidean spaces. Is it clear?
Are you writing something? Or-
No, I was just mentioning this one. Okay,
Oh,
okay, let me write it down. Hello?
no, it's okay. It's fine.
Okay, yeah. So this is once an example. Other example. So I hope it is clear why Rn is not Gromov hyperbolic. I mean, you can just see that the any if it, if you take any large equilateral triangle, the midpoint of a side is far from all the points on the other two sides. Let me just write it down so that it would be. So basically, the basically the midpoint the midpoint of a side on a large on a large triangle is far from all points on the other two sides. Okay, the other example is the Poincare model of the hyperbolic space. So the hyperbolic space. So this is the hyperbolic space means, let us say, don't confuse it with the Gromov hyperbolic. By hyperbolic space, I mean that it is upper half plane or the unit disk equipped with the Poincare metric is Gromov hyperbolic for delta is equals to, let us say, log 3. So, I mean, just to prove that it is Gromov hyperbolic is uh, that can be done in an easy way, but to get a better constant that delta equals to log 3 requires some effort. So I will mention this thing. So let us just see the proof of that it is Gromov hyperbolic. Okay, so let T be a hyperbolic triangle. Okay, and let R is equals to, let us denote this R basically depends upon R of T. Be the largest hyperbolic radius of a circle that fits inside a hyperbolic triangle. If it's inside a hyperbolic triangle. Okay, so let us see, we have this disk model. Let us say we have this disk model, and we are taking a geodesic triangle in this one. Let us say somewhere, okay, something like this, and we are looking for a hyperbolic uh, circle, means hyperbolic radius, largest hyperbolic radius of a circle that fits inside this hyperbolic triangle. Okay, and then it would be like, if we can show that like it is sufficient to prove that basically RT is less than or equals to log 3 by 2. So basically we want this delta to be log 3. So we need to prove that this largest radius of this hyperbolic triangle is basically less than or equals to log 3 by 2. Then what would happen in this case, that every geodesic triangle, so in every geodesic triangle, this is the largest radius we can fix. And hence if we take the log 3 neighborhood of this one and this one, the other side will be contained in this one. Okay. So this is the idea. I mean, and what we're going to do is that here is an uh, what we're going to do. Let me just let us say this is x, y, and z. Okay, so what I'm going to do is, let us because of the automorphism group, we can basically transform this to xy on the on the on the real axis. Let us say this is a and b, and basically what we have to do is like take any point u, okay, and map this u under this transformation to the point origin 0. And this since this is a conformal automorphism, it will preserve the geodesic. So this geodesic will be mapped to this geodesic. So that geodesic has to, in fact, that geodesic has to pass through origin, means that geodesic has to be straight line. So it can be like this, but then again we will rotate it. Okay. So ultimately, without loss of generality, we can assume that we have this triangle. The triangle of, like, the triangle which we are considering is like this. Let us say this is Z. Is it clear? Maybe Z some other point will be the, so I'm just denoting it as XYZ only. Sorry, let us denote it as. So I'm saying that without loss of generality, we can assume that this x comma y is on the real axis and this u is at the origin. Okay, is it clear? This will be conformal transformation. Okay, now now basically what we are going to do is we are going to assume that, let us say this is the triangle T. So this is your T. So we are going to assume that this triangle is nothing but this is a this is a this is a this is an ideal triangle. Okay, means it is something like uh, this. These are going to the these are going to touch the boundary of the unit circle, boundary of the unit disk. Okay, and why we can assume this thing, because if you increase the size of the one side, like this is kind of an observation, it needs justification, because it needs justification, but one has to do some hyperbolic trigonometry in that one. So it is like increasing the side length of any one side of T can only increase R. Okay, increase R. Okay, so so we may as well assume that T is T is T is an ideal triangle.
Can you repeat the what is the ideal triangle? Actually, I missed that point. Up to I have understood up to the point that it's enough to consider the geodesic triangle, whose one of the geodesic is in on the
Real line.
real line. That
Yeah,
that
yeah.
that part is clear.
Okay.
After that, what is ideal triangle?
So ideal triangle means like we are extending the sides of the geodesic. Okay. And the
Okay.
ideal triangle means it is touching the, like it is going towards the boundary, means it has the infinite length. Okay. What I mean is that if you see in the, let me just write on the another page. So if you see ideal triangle in the upper half plane, so geodesics going, like going to the boundary points, this is, let us say this part. Okay, this is a geodesic segment joining these 2 points, isn't it?
Hmm. Hmm.
Okay, now what we're doing is we are just increasing the size of this one. So a ideal triangle is kind of a geodesic, sides of an ideal triangle is a geodesic line. Okay, and one
Oh,
geodesic line.
sides of an ideal triangle.
Yeah, yes,
Okay.
sides of an ideal triangle is a like geodesic line. I mean, it is an infinite length and going towards the boundary.
No, so any geodesic triangle, uh, if I take any geodesic triangle, then its sides are geodesic lines. So it's not the point, I think. I'm not getting the point actually. What is example of a non-ideal triangle?
Non-ideal triangle means which just sit inside the domain. Like take any triangle, this will be the, this is not at present the ideal triangle, but it can be extended to the ideal triangle. Okay.
Okay, then how can it be extended? Then what is the definition of ideal triangle? It's geodesic line should that
And
the
you can
definition
see
of the
that,
ideal triangle.
so basically, as you can see that this side is kind of parallel to this side. They are not meeting anywhere. They are meeting at the boundary only. So in the space, they are like
Yes.
parallel to each other. Okay. So in the geodesic, so ideal
Okay.
triangle means every side is parallel to each other.
Every side is parallel to each other. Okay.
Yeah,
Then
and they are forming a triangle, kind of like they are meeting a, this is x y
oh,
and
that
infinity.
right. Okay. Here the curved line and the straight line both are parallel, right?
Yeah, yeah. This
Because
curve
they are
line,
not
so
meeting. Because
yeah, they are not meeting,
they
and
are
they
not
are
meeting.
geodesic. Yeah, and they are kind of
Yeah,
extended
yeah,
version
yeah.
of a geodesic.
And there are so many because that's
Yeah,
the
there are
whole
so many.
point. Violating the fifth postulate of Euclidean. That's the whole point.
Yeah,
You
yeah,
have so many non-intersecting parallel lines.
yeah, yeah,
Yeah. Now it's fine. Yeah. Okay.
yeah. So I mean, that's the kind of ideal triangle. Okay.
Okay. Each and every time when each sides are parallel to each other. This is the
Each sides are
definition.
parallel to each other. Yeah, and basically this can be possible like if they are converging to the boundary of the
Huh.
space, isn't it?
Huh.
Yeah.
This is always not necessary. It's not necessary. It's not intersection of boundary. Is it necessary that then it necessarily converges to the boundary if it's not parallel? If
Yeah,
you take the
because
ball model,
yeah.
hmm,
So, so in this one, a geodesic,
then
let us say,
up to extension,
up to
it should
extension, I'm
hit the
saying, yeah,
boundary.
yeah, it
Yeah,
should meet the boundary. This will
it
be
should
a,
meet the boundary.
yeah, this is an ideal triangle in the upper half, in the unit ball.
Upper half. So
Yeah,
each side should be parallel.
yeah, and each sides are parallel.
Okay.
This is the ideal triangle. So, okay, fine. So now what we can do is, just, okay, oh, sorry, what I have done, okay, x and y. So now what we can do is we will transform this one to the upper half plane model by mapping this x, y, and so making this x, y as -1 comma, this is minus 1 1. Let us say this is origin. Okay, so what we are going to do is we are going to convert this triangle into the upper half plane model. Okay, and in that case we will get the ideal triangle like this. Whether is it clear? So what we're going to do is, like, since we have 2 points x comma y, we can make it to the minus 1 and 1, and other point to the infinity, and we will have that this triangle will
Then
be
why shouldn't you start with upper half model? Then why should you start? Why do you starting with Poincaré ball model? When you start with upper half model, then do all the
yeah,
things
but
with that.
I was, yeah, exactly that I could have done, but I was trying to just make the statement that uh, starting with a geodesic triangle, like, sorry, we can start with not just with the geodesic triangle, we can start with an ideal triangle. So just to make that perception clear, I was starting with the ball model. Obviously we can start with, in upper half plane, just taking the ideal triangle.
Yes, that yeah, that.
Yeah, so
Okay.
that's what the, and doing so, will be like it will clear it, like this this method will be clear for ball model, simultaneously for upper half plane model also. So now here we have one result which I have to mention. This is hyperbolic trigonometry result, which says that so a circle, let A be a circle in the upper half plane, and suppose the uh, Euclidean Euclidean center Euclidean center Euclidean center of A is, let us say, A plus IB, and the Euclidean radius of A is R. Then the hyperbolic center hyperbolic center is A plus iota under root B square minus R square, and the hyperbolic radius R satisfies small r is equals to B tan hyperbolic R. Okay. Okay, fine. So now this is your minus 1 and 1, and so this is a kind of this is a T. Let us say this triangle is T. Just, let us say this triangle is T, and this triangle T, T is an ideal triangle. T is an ideal triangle with vertices of T are minus 1, 1, and infinity. Okay. Now the circle that maximizes R, what would be its Euclidean center and radius? So what we need is we need to like find out a circle here which can fit inside the first we will find out the Euclidean circle. So let us say this is our y-axis. Okay, fine. So we need to find out this one and its hyperbolic radius and what would be its so and what would be is sorry we need to find out the Euclidean center and radius and what would be the hyperbolic radius. So basically the Euclidean center will be 2I, okay, and this is your and this radius of this will be 1. So this will be the biggest circle we can fit inside this one. Okay, so a circle in the inner triangle means it has to be tangent to all the sides. Okay, means at one point it touches, and this has to be tangent to the the sides of the triangle. Okay, so this will be the circle is with 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 Euclidean center equals to 2I and radius equals to 1. Okay, now use this formula. This formula says that if we have a center a plus ib and this one, so basically what we have is a is we have a is equals to 0, b is equals to 2, r equals to 1. So hyperbolic center is basically under root 3I and 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 hyperbolic radius will satisfy 1 is equals to 2 tan hyperbolic r. So this implies r is basically tan hyperbolic inverse of tan 1 by 2. And what is this? This is basically log 3 by 2, its value. Okay, so this is the maximum hyperbolic radius of a circle which can fit inside that one. Okay, so this is what we wanted, and now take the delta as log 3. Okay, is it clear? Hello.
Yeah, it's fine.
Yeah. Okay. Okay, fine. So there's also one more way to prove the Gromov hyperbolicity that is quite immediately one will get, but I will just write it as an exercise. Use Gauss-Bonnet formula. So basically, what we have to do is like we have to, if geodesic triangles are not delta slim, we can fit a basically uh, we can fit a hyperbolic disk of radius delta by 2, which will have the area I forgot, like 4 pi sine hyperbolic square delta by 2 or 4, I guess. And according to formula, Gauss-Bonnet formula, this has to be at most pi, and from there we will get the bound on the delta. Okay, so use Gauss-Bonnet formula to prove the Gromov hyperbolicity, to prove the of Gromov hyperbolicity of hyperbolic space. Okay, so the next example is for, obviously, we have seen the cat K spaces, and basically we will see that they are going to be the Gromov hyperbolic. So example, and basically proof of this one requires this delta equals to log 3. So this is example 5. So if k is less than 0, then uh, every cat k space is Gromov hyperbolic, okay, with delta is equals to basically log 3 by root over k. I mean, the proof of this will is fairly simple. You just take the triangle in your model space. Obviously, that one has to uh, make this factor into the account. Uh, this one, because you're going to scale scale your hyperbolic space so that it will be have constant curvature k. So one has to multiply with this one, and then we have seen that hyperbolic space is delta hyperbolic with log 3. So we'll get this bound. It is just clear from the inequality of, yes. Hello. Any question? Okay. Mm. In particular, every complete simply connected Riemannian manifold with sectional curvature is bounded from above by minus k with k positive is Gromov hyperbolic. Okay, so we have all these examples of Gromov hyperbolic spaces. Okay. Uh, Fine. I think up to this everything is clear. Okay, so to construct other examples, like to construct more examples, we need to find out what is the invariance property of this delta hyperbolicity under some kind of suitable maps like isometry or quasi-isometries. And it will turn out that uh, Gromov hyperbolicity is preserved, is invariant under quasi-isometries. Okay, and the proof of this fact based upon the geodesic stability of Gromov hyperbolic spaces. So I'm going to mention that thing. So for that one, I need to. Okay, so we'll not talk about basically geodesics and
The Morse lemma.
yes, yeah, that Morse lemma. You said Morse lemma, no?
Yeah, Morse lemma.
Yeah. So I think okay. So let me just mention what do we mean by quasi isometry. So let lambda is greater than equals to 1 and mu is greater than equals to 0, and we have x comma d and y comma d dash be metric spaces. We say that a map a map f such that x to y is is lambda comma mu quasi isometry or quasi isometric embedding if for all x comma y belonging to x we have d of x comma y upon lambda minus mu is less than or equals to d dash of fx comma fy is less than equals to lambda d of x comma y plus mu. Okay, so this is the definition of quasi isometry, and remember that this map need not be continuous. I haven't write the continuity assumption in the map, so this is just a map, a function from x to y which satisfies this condition. uh, 1 comma 0, obviously a 1 comma 0 quasi isometry is simply an isometry onto its range. Okay, and we say that two metric spaces are quasi isometrically equivalent. This is an important definition because this is kind of called as the rough inverse of a map. Uh, so we say that x comma y are lambda comma mu quasi isometrically equivalent if uh, if there exists a lambda comma mu quasi isometry f such that x to y uh, with the property that if you take for every y belonging to this space capital Y, there is an x belonging to x with d dash of y comma f of x is less than mu. Okay, so in particular one way to see this is that in particular if f is on 2. Okay, I hope this is clear. Hello.
Yes, you are audible.
Yeah, so in particular, if f is onto means for every y there exists an x such that f of x is equals to y. Okay, means if f is onto means f of x is equals to y. So if you take the d dash of y comma this f of x, this will be at the point x, this will be 0. Okay, so this is going to be less than equals to this one. Oh, wait a minute, it is Oh, sorry. I'm writing this is I guess f of x. Yeah. Okay, so okay, fine. And in particular, if f is on 2, so fine. Okay. Uh, Now we have a notion of quasi-geodesic. Quasi-geodesic means it's just a lambda comma.
So if f is onto, then they are quasi isometrically equivalent, right?
Yeah,
According to your definition.
exactly. And that they are quasi-isometrically equivalent for any mu greater than 0, greater than equals to 0.
Yeah.
Yeah. Lambda comma mu quasi-geodesic in a metric space. In fact, I haven't mentioned this example. What are the examples of quasi-isometry? But these things are kind of like if we have biholomorphism between two domains in Cn or in particular C, then they are basically isometry with respect to the Kobayashi metric. Moreover, if we have quasi-conformal map between two domains in Rn, then this quasi-conformal map is quasi-isometry with respect to the quasi-hyperbolic metric. So in such way, we have the examples of quasi-isometries and isometries. Okay, so a lambda comma mu quasi-geodesic in a metric space is nothing but lambda comma mu quasi-isometry, quasi-isometric embedding gamma such that a comma b to x comma d. Okay. Note that in this case I did not write that this gamma is lambda comma mu quasi-geodesic gamma. So this note that I did not write that gamma is continuous. Okay, but there is no harm in doing so because we have the result which says that quasi-geodesics can be tamed. I will just mention that one. So note that right is continuous, but there's no in doing as the following result suggests. So it says that if we have any quasi-geodesics, means it is lambda comma mu quasi-isometric from interval to that space X, one can find a continuous lambda comma epsilon dash quasi-geodesics with the same endpoints and satisfy some particular properties that it's housed up distance between the it's how it is basically it is within the particular housed up distance with the earlier quasi-isometric embedding. So it is known as the taming. Uh, this is known as the taming because these are quite important ingredients in proving the Morse lemma, or we call it as geodesic stability. Let X be a geodesic metric space given any lambda comma mu quasi geodesic, so say gamma a comma b to x, one can find find a continuous lambda comma epsilon dash quasi-geodesic sigma such that a comma b to x with the same endpoints, such that, see here we have this continuous lambda comma epsilon quasi-geodesic. It means it becomes a curve. Okay, this is a curve, so that 1 epsilon dash is equal to 2 lambda plus epsilon. Second one is basically the length of sigma restricted to t comma t dash is nothing but lambda plus epsilon uh, lambda plus epsilon into d of sigma t comma sigma t dash plus lambda epsilon dash plus 3 into lambda plus epsilon. Okay, this is the second property, and the third property I will write here. Third property is like the Hausdorff distance between this gamma and sigma. This is basically less than equals to lambda plus epsilon. Okay, so this is quite a nice result. Basically, we can replace any given lambda comma mu quasi geodesic by a continuous quasi geodesic. Means it will be a curve. It will be considered as a curve. So there is no harm saying that a quasi geodesic is a curve. Okay, which satisfies the property of which satisfies this property. So quasi geodesic is a curve which satisfies this property. It's lambda comma mu quasi geodesic. Okay, so now we are going to mention the shadowing lemma, or this is known as the shadowing lemma, or this is also called the geodesic stability. It's also called the Morse lemma. It says that suppose x comma d is a Gromov hyperbolic space with delta greater than equals to 0, then for any lambda greater than equals to 1 and mu greater than equals to 0, there exists a constant m which only depends upon delta, lambda, and mu, nothing else. Such that if gamma is from A1 to B1 to x is lambda comma mu quasi-geodesic, and let us say sigma is from A2 to B2 to x is a geodesic with gamma A1 is basically sigma A2 and gamma B1 is basically equals to sigma B2. Sorry, what is this? Gamma A1 is sigma A2 and gamma B1 is basically sigma B2, yeah, with the same endpoints. Then basically the Hausdorff distance between the images gamma of A1 comma B1 and sigma of A2 comma B2, this is always less than equals to m. Okay, and an immediate
So,
consequence of, yes,
no, you.
yeah.
No, actually, I want. wanted to ask that this lemma actually says that any distance, Hausdorff distance between uh, any geodesic whose endpoints and start points are same is the distance is less than equals to n. So
Yeah,
my
exactly.
question is that if I take any of r positive and
Any R, okay.
any r positive
Mm-hmm.
mm, and consider a r neighborhood of the quasi geodesic lambda comma mu.
Mm-hmm. Mm-hmm.
Then is it true that there will exist a geodesic with the same initial and the final point inside that quasi geodesic region? Is it true?
Oh, means you are asking the existence of a geodesic between in that
Close
neighborhood.
enough to the close enough to the neighborhood to the given quasi geodesic.
Okay, this is uh, no, not really. No, we cannot say this one because like there are spaces. So okay, so there is spaces. Let us say
No,
uh,
even if geodesic ball model, in if I consider the Poincare ball model with respect to the hyperbolic.
yeah, if the geodesic exists between those 2 points, then it will be in the in no, but this r already depends upon this delta lambda mu. You cannot just take any r. Like if you take see, like if you take a quasi geodesic with the lambda mu with the given
Does there exist any special form of the quasi geodesic for that model?
sorry.
Like, মানে, does there any explicit formulas or forms of quasi geodesic in Poincare ball model? Like the geodesics are with the real lines or the if it's the half circle touching 90 degrees at the
Yeah,
boundary like that.
yeah. So
Even if I assume that your
I don't know
the
whether you
this
are
is
coming. Yeah. Yes.
your if I assume if I also assume that it is bilipsis, not the mu is zero. If I take
Bilipsit too.
and if I assume the quasi geodesics are bilipsis, that means I want to
Okay.
mean
Okay.
that
Understood.
mu is
Yeah.
yeah
Mu
zero.
is zero. Yeah.
Hmm.
Then
Then also the thing it can be approximated by geodesic that thing actually. Any neighborhood that contains a geodesic.
okay. Yeah. So in that case, basically, so there is a result which says that if you take any geodesic, any hyperbolic geodesic is
Yeah.
basically a quasi hyperbolic quasi geodesic, and
So
any
what you say? What is it?
like there is a
Any?
result there is a result which says that I will mention that result later on, but I don't know whether time will
Okay,
permit me or not. So if you take any
but
geodesic, so if you take any hyperbolic domain in C, okay.
okay, okay,
Now for this hyperbolic domain we have two metrics. One is hyperbolic metric and one is quasi hyperbolic metric. Okay.
okay.
The
Uh,
the result says that if you take any 2 points x comma y and take the hyperbolic
uh,
geodesic with joining x comma y,
uh,
then this is basically going to this is a hyperbolic geodesic. This is basically quasi geodesic, and the converse is also true, like quasi geodesic, and the converse is
okay,
also true, which says that if this is quasi hyperbolic geodesic, then it is the hyperbolic quasi geodesic, means it is a quasi geodesic with respect to the hyperbolic metric. Now coming to your question, as far as I understood, you want to say that if we have any 2 points x comma y, and if we fix any r neighborhood of this one, let us say this is the r neighborhood of this point.
right, right.
Okay, so this is a quasi geodesic,
Mm,
and this is, let us say, r neighborhood. Okay, so quasi geodesic with the, let us say, lambda comma mu constants are given to us.
lambda comma zero you can take for that.
okay, lambda comma 0. Okay, fine. Uh, okay, it's a bi-Lipschitz means. So you want to ask whether there exists a geodesics joining these 2 points which will stay inside this neighborhood, isn't it?
Right. Right. This
Okay,
R is arbitrary.
okay, fine. So uh, okay, okay, so and here R is arbitrary, like we are choosing that R. And you said if this is bi-Lipschitz, okay, lambda comma mu, if it is lambda comma mu means then it will exist. Hello?
What you say?
No, no, you said something about the bi-Lipschitz. Can you
No,
please
no.
repeat that?
I just wanted to. No, I have not given any result. No, I am just asking that even if I assume that mu is 0 and the distance is, no, the model is a Poincaré ball model,
Mm-hmm.
then whether is it true, approximable by geodesic? I mean, what you have just told, that is true or not? That's what I am asking.
I I don't really think so, because suppose okay, so in the Poincaré
So
disk
you
model,
think that it's
uh,
not
so,
likely to
so
be whole, right? You think?
sorry,
No, you think it may not be true.
this is not true, I guess.
Oh, oh,
Yeah, okay, so I'm just explaining that one. So let us
okay,
so in the Poincaré disk model, you know that geodesic between any 2 points geodesic is unique.
right.
Okay, so suppose for this R we have this geodesic. Okay, if we take the R smaller than this one, and let us take we are taking this neighborhood now, then for this one there is no geodesic joining x and y, isn't it? Because the geodesics are unique, and
Oh,
that
oh,
is only
oh.
x and y. You got the
Hmm.
point?
Yes, yes.
Yeah.
Fine.
So I'm that's quite like, otherwise we
Now,
are taking
whenever one geodesic will exist, you will measure the minimum distance between that and take the r less
exactly
than that, right?
exactly. So other geodesic is not there. Like there is no geodesic, and even this is quite a demanding thing to ask. Like kind of like we want in every neighborhood there is a geodesic, which is kind of I
Bad.
don't know.
Okay,
Yeah.
okay. Thank you,
Yeah.
thank you. Yes, thank you.
Yeah.
I've understood.
Yeah. Okay. So uh, the next thing is to okay. So this is geodesic stability, and basically the converse is also true, and that is a result by Mario Bonk. The converse says that if we have this thing like we take a quasi-geodesic, and there exists an M, so that geodesic will lie in that neighborhood, then the space is Gromov hyperbolic. Means this geodesic stability criteria characterizes Gromov hyperbolicity. Gromov hyperbolicity gives geodesic stability, and geodesic stability gives delta hyperbolicity. So the converse is also true. So converse is also true. Is due to this is result by Bonk. Okay, now we will come to our main result, which we want, the invariance. So this is theorem. Invariance under quasi-isometry. Okay, so let x and y be a geodesic metric space, and let f such that x to y be quasi-isometry. So whenever I'm saying quasi-isometry, it means that it follows the definition which I wrote earlier. And whenever I say quasi-isometrically equivalent, means that second condition is also there. And in particular, one can take the ontoness condition. So in this case, if y is Gromov hyperbolic, then x is Gromov hyperbolic. Okay, that is, if y is delta hyperbolic and f is quasi-isometric given by the data, let us say lambda comma mu, then x is delta dash hyperbolic, where delta dash depends only upon delta, lambda, and mu. Okay. Furthermore, if x and y are quasi-isometrically equivalent, quasi quasi-isometrically equivalent, then x is Gromov hyperbolic if and only if y is Gromov hyperbolic. Okay. So in particular, if we have a quasi-isometry which is on two between two spaces x and y, then they are simultaneously Gromov hyperbolic. Means x is Gromov hyperbolic if and only if y is Gromov hyperbolic. So I hope this is clear now. Okay. Let me just quickly mention some reformulations which one can go through some book. I'm not going to discuss this on. So some reformulations are also available, which are like delta thin triangles. This is kind of a flattened version of a tree, defined using tripods. Second one is Gromov product, and 4-point condition. And the third one is linear isoperimetric inequality. Okay, so for geodesic spaces, for geodesic metric space, all are equivalent. One can go through the Britson book and it is there. Okay, so these are some reformulations of Gromov hyperbolicity. Okay, fine. So up to this, I think everything is clear, because we are now going to move towards the uniformization technique introduced by Bonk, Heonen, and Koskela. So if any doubt, please let me know up to this point. Okay, if not, let us move to the BHK uniformization. Okay, so what do we mean by this uniformization technique? So as we see that the unit disk, if you take the unit disk, this is two conformally related lives. Okay, one is incomplete space with respect to the Euclidean metric. Okay, and one life is as a complete Riemannian two manifold of constant negative curvature. Constant negative curvature. Okay, and these two lives are conformally related, because this Riemannian metric is conformally equivalent to this metric, Euclidean metric. So they are conformally related. Okay, what we're going to see is that the same kind of basically we are going to see that the same kind of concept is available for in general Gromov hyperbolic spaces. Okay, in the general setting, in the more general setting, the same kind of concept is available. And for that one, what so in the BHK uniformization, this incomplete space is nothing but the uniform space, uniform metric space, and and at this place, this it is general Gromov hyperbolic space. And what BHK has shown that there is a one-to-one conformal correspondence between the quasi-isometric class of proper geodesic, roughly star-like Gromov hyperbolic spaces and the quasi-similarity class of bounded locally compact uniform spaces. So this was their main theorem in that paper, which says that there is I will just mention a uniformization procedure, like how what is the uniformization procedure for the Gromov hyperbolic spaces, because the proof requires a lot of technical stuffs. Conformal correspondence between the uh, quasi-isometry class of proper geodesic Gromov hyperbolic spaces and quasi-similar class of bounded locally compact uniform spaces. Okay, so this is our this is the main theorem. What is the procedure to get to this theorem? Okay, so I hope the idea is clear what we are going to do by the uniformization. Okay, we are going to basically uniformize a Gromov hyperbolic space into a uniform space. Okay, like we are going to conformally deform this space. And how we are going to do this one is like this will be uniformization procedure. Okay, so what BHK did is like let x comma d be, let us say, I will denote RC as rectifiably connected metric space. Fix a base point W belonging to X and consider the family of conformal deformations of X by the densities rho epsilon X is nothing but exponential of minus epsilon, and we are taking d x comma w. So this is our rho. If you remember the way we define the conformal matrix, taking the rho, this is the same way we are defining. So this is our densities. Okay. Now denote by x epsilon. This x epsilon is nothing but x comma d epsilon. Okay, where in obvious sense d epsilon is a metric induced by this density, like distance function, where integral over gamma rho epsilon x, and this is ds. So ds is basically the arc length parameter for the metric D, is the length element for the metric D, and where the infimum is taken over. Sorry. Uh, where the infimum is taken over all the rectifiable curves joining x and y. Okay. So now we have deformed x into another metric space which is x comma d epsilon. Okay. So here are some properties. I will mention it as an exercise because this can be proved without going through the paper. So the first thing is, if x comma d is geodesic, then x epsilon is always bounded. So we get that this is a bounded metric space once we assume that x comma d is geodesic. Of course, this is what we are going to do, as like we are going to assume that xd is a geodesic metric space. We have the Harnack-Type inequality. So prove the following, which is exponential of minus epsilon d of x comma y. This is less than or equals to rho epsilon x upon rho epsilon y, and this is basically, it's uh, in fact this is fairly easy to prove. Just use the triangle inequality. So this is known as the uh, Harnack type inequality. Okay, so this is for x comma y belonging to x and epsilon positive. Okay, so use the triangle inequality to prove this one. And the the third property is, if x comma d is geodesic, then it follows that the identity map. So we have the identity map x comma d epsilon to x comma d. This is locally a quasi isometry. So this is local quasi isometry, and in particular, this is a x comma d epsilon is rectifiably connected. Because this is rectifiably connected, so in the local version you can take it is a quasi isometry, so that will be again rectifiable. So in particular x epsilon is rectifiably connected. Okay, now we'll mention the uniformization theorem. This says that let x comma d be rectifiably connected metric space if x comma d is proper geodesic Gromov, let us say Gromov hyperbolic. I will write Gromov hyperbolic, and I will also mention that this is for some delta. Okay, this is for some delta. Then the conformal deformations x epsilon, which is x comma d epsilon. So these are bounded, this we have already seen. I have written the exercise. A delta, where A only depends upon delta, uniform space. I haven't mentioned what is uniform space, but I will just mention uniform space for epsilon greater than 0 and epsilon naught. I mean, there exists an epsilon naught which also only depends upon delta. So if you take any epsilon less than equals to epsilon naught, this will be a uniform space. Okay. Here one thing is to like obviously prove that this x this x epsilon is going to be non-complete, and hence it has observed that since we are taking x comma d as a proper metric space, this x epsilon is going to be locally compact, because proper implies locally compact, and this is a conformal deformation. Identity map is local quasi-isometric. This is going to be uh, locally compact. Moreover, x epsilon is non-complete, and hence if we consider the metric boundary of it, it is non-empty. So this is non-complete. Prove, this is so provide a hint. So just take any sequence tending to infinity in x along a geodesic ray. Okay. So this is our uniformization theorem, which says that every proper geodesic Gromov hyperbolic space can be conformally deformed into a uniform space. Okay. Let me just quickly mention what is uniform space. This is basically, geometry will be more clear if we consider the domains in Rn, but let me just quickly mention. This will be the last thing. Uniform space. So let x comma d be a rectifiably connected, locally compact, and non-complete metric space. I'm assuming all this because to say that complete metric space, so the metric boundary is going to be non-empty. Okay, and hence we can define the quasi-hyperbolic metric on it. Okay, so the uniform space definition is if if there exists a constant c greater than equals to 1, such that uh, every pair of points x comma y belonging to x can be joined by a curve. So this is can be joined by a curve. There is no can be joined by a rectifiable curve. Rectifiable curve gamma, such that first one is minimum of the length of gamma restricted to uh, length of gamma from x to z, and the length of gamma from z to y. This is less than or equals to c into delta omega of z, which distance to the boundary of z. Second one is length of this curve gamma, means this is the metric length of gamma, is less than or equals to c into the distance between these 2 points. So this is known as the quasi-convexity condition. And this is known as the cone arc condition. Okay, anyway, since I wanted to explain more on this one, but we don't have enough time. I will mention all these things in our in the so there will be last lecture, which will be a extra session. So in that session, I will mention all these things. Okay, so this is what we mean by uniform space. Okay, so I'll stop here. Any questions?